Hi, welcome back to the lecture series on abstract measure theory with course code MMT, MTH701 and MMTE305. In the previous lecture, we have discussed when the function of measurable function is uniformly integrable, and we have also stated a theorem, which we call the Vitali convergence theorem, in which we have seen that if given a collection of integrable function, given a collection of functions which is uniformly integrable, then we can pass the limit through integration. That we have discussed in the previous theorem. So now in this lecture we will discuss some more properties of monotone functions. So here we will state the theorem in which we will see that the function is absolutely continuous if and only if it's the divided difference function is the collection of divided difference functions is uniformly integrable. So let's state this theorem here. Let the function f be continuous on closed and bounded interval. Let the function f be continuous. Let the function f be continuous on closed and bounded interval AB. Then f is absolutely continuous on AB. Then f is absolutely continuous. Absolutely continuous on AB. So this is true for continuous functions. Okay, this function f is absolutely continuous on AB if and only if the family of divided difference functions divided difference functions if and only if the family of divided difference functions, this family HFK with 0 less than h less or equal to 1, if and only if this family is uniformly integrable, is uniformly integrable on AB. So this this uniformly integrable is already discussed in our previous lecture. So here we will see that this function, a continuous function f, is absolutely continuous if and only if the family of divided difference functions, this family is uniformly integrable over AB. Assume this function f, assume this collection of divided difference functions is uniformly integrable. Assume the collection of those functions divided differences of f 0 less than h less or equal to 1 is uniformly integrable. So here it is given that f is continuous function. Okay, in both the for converse also the f is given to be absolutely continuous. F is given to be continuous function. But for converse we don't need f to be continuous, because for the converse we have f is absolutely continuous function, so therefore it's continuous always. But for this part where we have assumed that this collection is uniformly integral, so we must use this assumption that f is continuous function. So this f is continuous function, and that class of divided difference functions is uniformly integrable over AB. Let epsilon be any positive number, then by definition of uniformly integrable, let epsilon be any positive number. It's a positive number. Let epsilon be any positive number epsilon is a positive number, then by definition of uniformly integrability we can choose delta positive, choose delta positive such that the integral over E of the divided difference function f is less than epsilon by 2 if measure of E, if Lebesgue measure of E is less than delta for 0 less than for 0. This is true for each function in this collection. Okay, for each 0 less than h less or equal to 1. So we claim that this delta respond to the challenge regarding the criterion for f to be absolutely continuous, because we need to show that f is absolutely continuous. For this we show that for each epsilon positive there should exist a delta positive satisfying that property. Okay, so we show that this delta and this epsilon will work for the function to be absolutely continuous. Okay, so for this we choose any disjoint collection of finite disjoint collection of open intervals such that the sum of the lengths of those open intervals is less than delta, and we will show that the variation is less than epsilon. So let's choose any finite disjoint collection. So let ck dk k runs from 1 to n be any finite disjoint collection of open intervals such that the sum of the lengths dk minus ck is less than delta. Okay, so we show that for f to be absolutely continuous, we show that summation k runs from 1 to n mod of f of dk minus f of ck is less than epsilon. Okay, we have this, we have already verified. We have this integral ck dk divided difference of f, it's equal to f of dk minus f of ck. This we have already verified. Okay, for all 1 less or equal to k less or equal to n, this we have already verified. This one. Now actually we need to find this sum actually. this f of dk minus f of ck. Sorry, it's actually equal to not. It's not equal to this. It's equal to the average value. Sorry. Sorry. It's the average value of f at dk minus average value of f at ck. It is equal to average value of f at dk minus average value of f at ck. Okay, now let's try to find out this sum, because k varies from 1 to n. Now summation k runs from 1 to n mod of average value of f at dk minus average value of f evaluated at ck. This sum, okay, apply mod here, then I have taken the sum, so it's actually equal to summation k runs from 1 to n. What's this this mod of that difference, which is equal to the integral ck dk divided difference of f. Okay, now we know that the mod of integral is always less or equal to the integral of mod, so it's less or equal to summation k runs from 1 to n integral ck dk mod of divided difference of f. Okay, it's less or equal to this. So this one, since they are disjoint intervals, so this summation is actually equal to the integral over the union of the intervals ck dk k runs from 1 to n mod of the divided difference. But this one, measure of this set is less than delta, so therefore this integral is less than epsilon by since this collection is uniformly integrable. Here you can see the definition of uniformly integrable. It is this one. So this divided difference over the set E is less than epsilon by 2 if the Lebesgue measure of the set is less than delta. And here you can apply this. Since the Lebesgue measure of this set is less than delta, because they are disjoint, its Lebesgue measure is the sum of the lengths of the intervals. It is d1 minus c1 plus d2 minus c2 plus so on plus dn minus cn, which is less than delta, as you can see it here, because we have chosen this collection in such a way that the sum of the lengths of these intervals is less than delta. Here you can see it, this summation is less than delta. So I can write here this one, this is less than, I can write it less than epsilon by 2 as the Lebesgue measure of this union k runs from 1 to n ck dk, which is it's equal to the summation k runs from 1 to n dk minus ck, and this one is less than delta. Or you can write the name of those equations here, so that we can call those equations here. So I will write here, name it here, say 1. Okay, so it's actually from 1 by this, all is by 1. Okay, so thus we have obtained this one, this average value is less than epsilon by 2. Okay, so thus summation k runs from 1 to n mod of the average value of f evaluated at dk minus average value of f evaluated at ck is less than epsilon by 2. This is less than epsilon by 2. Now we will see that this sum of the difference of these average values is actually the sum of the variations. So here for this we have to check this when this h is approaching to 0, this average value, what will be this average value equal to. So let me expand this one first. Name it here 1, okay, name it here 2, this one. So let's try to find out this. We have this average value evaluated at f of dk, or you can simply check this one, then this follows on similar lines, or you can calculate the difference as well. It's no harm, or you can calculate the single value, then apply the same procedure to this one. Okay, average value of f at evaluated at ck, evaluated at ck. So this one it's equal to the integral, it's equal to 1 over h by definition of average value. It's equal to the integral, it's equal to the integral dk to dk plus h, okay, by definition of the average value of the integral evaluated at dk f of t dt. Since our function is integrable, since our function is continuous, here we use the continuity of f. Okay, since our function is continuous, so it's equal to, by mean value theorem for this integrable function is it's equal to f of c1 into the length of this interval, that's equal to h. What is this c1? This dk is less than c1. I can write it as ck here, okay, so to be precise, dk is less than ck. I will write here ak because ck is already there, so I will write here ak. dk is less than ak is less than dk plus h. Okay, so these two will go, so it's equal to f of ak, where this dk it's less than ak and ak is less than dk plus h. So that's the average value of f evaluated at dk. Now letting h approaching to 0, this ak will approach dk, because whenever h is approaching to 0, this ak is approaching to dk, and whenever ak approaches to dk, f of dk will approach to f of ak. It's here ak, right here, it's ak here. So this implies limit h approach to 0, average value of f evaluated at dk is equal to limit h approach to 0 f of ak, but whenever h approaching to 0, this ak it will approach to dk, so whenever ak approach to dk, this f of ak will approach to f of dk, as f is continuous, so this limit is equal to f of dk. Similarly, limit h approach to 0, average value of f evaluated at ck is equal to f of ck. So these limits are equal to f of dk and f of ck respectively. So here you can you can see. Now here you can apply this limit and you can write this average value of f at dk is equal to f of dk. This will be f of ck. So letting h approach to 0 in 2. Now letting h approach to 0. Letting h approach to 0 in 2, we get summation k runs from 1 to n f of dk minus f of ck is less or equal to epsilon by 2, which is less than epsilon. So thus whenever we have finite disjoint collection of open intervals such that the lengths of those intervals is less than delta, then this variation with respect to those intervals will be less than epsilon. So this implies that this f is absolutely continuous. F is absolutely continuous. F is absolutely continuous. Now we prove its converse part. Conversely assume that this f is absolutely continuous. we show that this class of divided difference functions 0 less than h less or equal to 1 is uniformly integrable. That is for each, we show that is for each epsilon positive. We show that there is delta positive such that the integral over E of the divided difference of f is less than epsilon if Lebesgue measure of E is less than delta. If Lebesgue measure of E is where E is any measurable subset, where E is any measurable subset of interval a, b. Okay. So we show that for each epsilon positive there is delta positive such that for every measurable subset E of AB, this holds. This is less than epsilon. Integral over E of the divided difference function is less than epsilon if the Lebesgue measure of the set E is less than delta, where E is any measurable subset of AB. First, we prove this for those measurable subsets which are the finite disjoint union of members of open intervals. So assume that case 1, okay. Case 1, if E is equal to union ck dk, k runs from 1 to n. If you equal to this is a union of finite disjoint open intervals. Okay, if E is the union of finite disjoint open intervals. Now let epsilon be any positive number. We need to find delta positive. Let epsilon be any positive number. Okay, So since our f is absolutely continuous, we can find delta positive. Let's suppose that delta positive, we can choose delta positive that respond to the epsilon by 2. Choose delta positive respond to epsilon by 2, respond to epsilon by 2 regarding the criterion for f, regarding the criterion for absolutely continuity of f, as f is absolutely continuous. Okay, absolutely continuity, sorry. Okay, let epsilon be any positive. Now we can choose delta. Since f is absolutely continuous, we can find delta positive for each epsilon positive. Let's choose delta positive for this epsilon by 2. Absolutely continuity of f. Okay, f is absolutely continuous, and it's absolutely continuous on this interval, a to b plus 1. So we use that extension actually. So now by change of variable formula, by this you verify yourself. Okay, by change of, as we have already verified one, that one of our formula by using change of variable formula, by change of variable formula, but by change of variable formula for the Riemann integral, for the Riemann integral, and use some sort of cancellation also, as we already explained, and some sort of cancellation, you will see this integral u to v divided difference of f, it's equal to 1 over h integral 0 to h f g of t dt, where this g of t is equal to f of v plus t minus f of u plus t. Okay, so you can easily verify this formula. This divided difference is equal to 1 over h 0 to h f of v plus t minus f of u plus t. Okay, this you verify yourself. Okay, verify it. So you have to use some substitutions here, and then you have to add and subtract certain things, some integrals, so that you will get this formula. Okay, now if this collection of ck dk's, k runs from 1 to n, is a disjoint collection of open subintervals, is a disjoint collection of open intervals in a b, then we have this then we have this integral over e, where e is this union actually, then integral over e of divided difference f, it's equal to summation k runs from 1 to n integral from ck to dk, okay, from ck to dk of divided difference of f. That's equal to summation k runs from 1 to n. What's this integral? Ck to tk, it's equal to 1 over h, integral 0 to h, integral 0 to h, and you can see this one, you can apply the previous formula actually. This is f of v plus t minus f of u plus t. Here v is dk and u is ck, so it's equal to f of v minus dk plus t minus f of ck plus t. Okay, that's equal to summation k runs, sorry, I will write here, that's equal to 1 over h 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 1 over h, that's equal to 1 over h integral integral 0 to h. Then you can write here summation k runs from 1 to n f of dk plus t minus f of ck plus t. Okay, so it's this, and that's equal to 1 over h integral 0 to h. You can write it as g of t, where g of t is equal to summation k runs from 1 to n f of dk plus t minus f of ck plus t. This is your g of t. Okay, where this t varies from 0 to 1 actually, this should be 0 less or equal to t less or equal to 1. Okay, this t varies from 0 to 1 actually. This should be noted here. This t varies from, and this here, this t is 0 less or equal to t less or equal to 1. Okay, so this we have seen here. Okay, so g of t is equal to this, so this is our integral actually here. What is this? The integral of divided difference over e is equal to that summation, that sum. Okay, so now we need to show that actually our function f is this collection is actually uniformly integrable. So therefore, if the summation k runs from 1 to n dk minus ck is less than delta, this implies summation. That means actually it means that Lebesgue measure of E is less than delta. If Lebesgue measure of E is less than delta, means this actually, because E is the union of those intervals actually. This implies summation k runs from 1 to n. This is a dk plus t minus ck plus t is less than delta, because this t and t will go. But this function is absolutely continuous, so that means summation k runs from 1 to y, t is lies between 0 and 1, f of dk plus t minus f of ck plus t, this sum is less than epsilon by 2. This sum is less than epsilon by 2, less than epsilon by 2. Okay, so let's apply this here. Here we have this integral is equal to 1 over h 0 to h g of t, where this g of t is that sum, and that sum you have seen that sum, this is actually a modulus. Sum of this modulus is less than epsilon by 2. So therefore integral over e of mod of divided difference this we will see this is equal to, so let me again check the previous page. This is equal to that summation okay, so this one is equal to this one is equal to, without we don't use actually mod here, so it's equal to, so here I will write this without mod. Okay, so I will explain why I am not writing mod here. Okay, so this is the mod, this is the divided difference which is equal to the this is your again there is no need of mod. Don't write here mod, because initially we must assume that this function f is actually monotonic increasing. Okay, so we don't write mod here. Our function f is monotonic increasing. Okay, so function f is monotonic increasing. So this divided difference which is equal to 1 over h integral 0 to h of that one that g of t, where g of t is this sum, g of t, it is summation k runs from 1 to n, this we have verified, it is equal to this one, f of dk plus t minus f of ck plus t. Okay, and this we have seen it's less than epsilon by 2. So I am not writing mod anywhere here because our function f is absolutely continuous. So this if it is absolutely continuous then it's a difference of two monotonic increasing functions. So conversely assume that f is absolutely continuous, therefore it must be the difference of two increasing functions. So if it is difference of two increasing functions, we can assume that this f is, our function f is increasing function. So here I should write it. So therefore we shall we assume that f is increasing. Okay, we assume that f is increasing. Okay, this is our assumption. So if we prove this theorem for increasing function, then it will be true for difference of two increasing functions, and hence it will be true for any absolutely continuous function. So this function is monotonic increasing, that's why we don't need to write mod anywhere here. So I can erase this mod here as well. We don't need of these mods here because our function is monotonic increasing now. Okay, I don't need to write mod for the converse part. Okay, for converse part I don't need to write mod. Okay, so we are here. This as f is continuous, where is page? This one is less than delta, so it's less than epsilon by 2, which is less than epsilon by 2 here. Divided difference is less than epsilon by 2. Okay, so this divided difference is less than epsilon by 2, which means that the function, this collection is uniformly integrable. So this implies the collection of divided difference functions of f is uniformly integrable. Uniformly integrable. Okay. So now our next theorem is the criteria for the function f to be absolutely continuous. Again, not that in this theorem we will see that if f is absolutely continuous function, then its derivatives exists almost everywhere, and its derivative is actually integrable over the interval. That's the next theorem. Okay, for absolutely continuous functions. Let the function f be absolutely continuous on closed and bounded interval. Let f be absolutely continuous. Let f be absolutely continuous on closed and bounded interval ab. Then f is differentiable almost everywhere. Then f is differentiable almost everywhere, and its derivative f dash is integrable, is integrable over AB, and this integral a to b f dash is exactly equal to f of b minus f of a. Okay, this is our theorem. Proof. So assume this f is absolutely continuous, is absolutely continuous. So therefore f can be expressed as the difference of two increasing functions. And by Lebesgue's theorem, every increasing function is differentiable almost everywhere. So therefore f is differentiable almost everywhere, because f is difference of two increasing functions. Therefore f is differentiable almost everywhere on AB. F is differentiable almost everywhere on AB. So thus the limit. Thus this sequence of f, this sequence converges finite-wise to f dash almost everywhere, because its limit, whenever its limit exists, it will be equal to f dash. But whenever this f dash and its limit is f dash at that moment, and this f dash exists almost everywhere. Okay. Also this collection of divided difference functions 1 over n of f is uniformly integrable, because f is absolutely continuous by previous theorem, is uniformly integrable. So therefore we can apply Vitalik convergence theorem. Therefore we can apply Vitali that we have stated in our previous theorem, in our previous lecture, Vitalik convergence theorem, that is limit and approach to infinity integral a to b divided difference on this class, on this collection which is uniformly integrable, it's equal to a to b limit and approach to infinity that divided difference 1 over n of f. And this limit, we know that it's equal to f dash, actually integral a to b f dash. But now we need to check this limit. What's this limit? So this implies limit and approach to infinity, and this one, we know that this one, it's equal to f of b plus 1 over n minus f of this average value, actually limit average value of f evaluated at b, it's here 1 over n, okay, 1 over n minus average value 1 over n of f evaluated at a. And this one, when you apply the limit, as I already explained, because this average value is actually the integral, this average value is also the integral, and then you can apply the mean value theorem for integral. And after that, letting this n approaching to infinity, you will see this limit, this is equal to f of b, and this one is equal to f of a. This already explained. If you want to see, I will select the previous page where I have verified it. Okay, let me see it. I think it is where it is. This is okay. Here you can see this average value of f at dk. It's equal to. You can see this is equal to. Finally, it's equal to, when I apply the limit h approach to 0, it's same as the n approaching to infinity 1 over n. Okay. If I replace this h by 1 over n, then h approach to infinity means same that n is approaching to infinity. Okay. So this is one and the same thing, but this limit, okay, oh, it's not here. This one, then there should be next page of it. Oh, that's not here. Sorry, that page is not here. Okay. So this limit, yes, that limit h approach to 0 f of dk, it is equal to limit h approach to 0 f of ak, which is equal to f of dk. So this limit is equal to f of dk whenever this is approaching to 0. This is approaching to 0. So in our case, we have this limit and approach to infinity, average value 1 over n f of b minus average value 1 over n f of a, it's equal to integral a to b f dash. So whenever n approaches to infinity means that whenever n approaches to 0, so this will be equal to f of b and this will be equal to f of a. It's equal to f of. So here we are using actually the continuity. Since our function f is absolutely continuous, therefore it's continuous. So this proves this theorem completely this way. Okay. Now our next theorem we'll have to discuss indefinite integral, and we'll see that the function f is absolutely continuous if and only if it is indefinite integral of some functions. That will be the last topic of this section. After that we are going to the next unit. So it will complete in just one or two lectures. It will take 1 or 2 lectures now. So after that I will take the second unit of this course. So the last section of this course of this unit is the indefinite integral, and we will see that the function f is absolutely continuous if and only if it is indefinite integral of some function. And we will also see that the indefinite integral of a function is always absolutely continuous.